This is a really slow way, essentially, to change the gradient of positive. It's not slow, but it could be a lot quicker, couldn't it? You're going 3 steps forwards, 2 steps back, if you like. So you're moving 3 positive ions out, moving 2 positive ions back in. So you only get a net movement of 1 ion from doing that. Anyway, it works. And that's an example of the primary active transport. You can get that with uniporters, not the sodium potassium pump, but you can get primary active transport, really ATP driven pumps with this. Symporters and antiporters, no, you don't tend to get, I suppose antiporters, you can get 2 in, 2 out with the sodium potassium pump. I think that might be an example. But yes, there's a lot going on. Oh no, that's a secondary active as well. Does it use ATP directly, or does it use the energy stored in the gradient? No, uniporters don't tend to use the ATP directly. Symporters and antiporters do. There are so many different channels. There's all the different molecules, so it is quite difficult keeping track of what's going on. And it's best almost to look at each one individually if you're studying it. If you're studying movement across the membrane of any particular substance and you're going into more detail and more depth, look at each protein across the membrane individually and look at what it's doing and learn for that molecule. Try not to worry too much about this at the moment. This is quite detailed and a bit above the level. I suppose you're not going to be asked a lot about this sort of stuff at this level. Yes, you need to have a sort of background of what's going on because we are going to use movement across the membrane when we talk about nerves and muscles soon, but don't worry too much about these definitions. They're not massively important at the moment. Just be aware that there are different types and they do different things, but you don't need to memorize them or anything like that for now.